A brief review of Newton's first law. No net force, no change in motion. And no change in motion, no net force. Change in motion is a change in speed or direction. You have to have force to change your state of motion. Then we talked about net force. Net force is you add up all of the forces, take up to be positive, right to be positive, and then subtract out whatever goes in the opposite direction. So how does a net force change motion? Here are some rules of thumb. If the net force is the same direction as the object's velocity, the object will speed up. So if your force and your velocity are both pointing to the right, you're going to speed up. If the net force is in the direction opposite of the velocity, you're going to slow down. If you're applying a force to the right and the car is moving to the left, you're going to slow down. Representing forces. Drawing arrows to show forces acting on the object. So how does net force change motion? Here are some rules of thumb. In both cases, we draw an arrow to represent each individual force acting on the object. The arrow is labeled with a type of force, whether it's F sub G, F sub W, or mg. I would prefer you do F sub W, F sub N, F sub capital T, F sub F, F sub S, F sub D, or F sub A, depending on the type of force you're dealing with. Now we draw longer arrows for stronger forces. We've already been working with this idea of arrows and vectors, and when we were doing motion diagrams, we were drawing these arrows above the dots on velocity, and the arrows were small, and if the object was speeding up, the arrows started growing bigger. It's the same idea here. Bigger arrows, bigger forces. We draw the arrow pointing in the direction the force acts. A free body diagram treats the object as a particle. So it takes this eraser and shrinks it down to a point particle, which is a theoretical thing that doesn't actually exist. It takes up no space and has no volume. So it just shrinks everything down, and we don't have to worry about anything else acting on it other than what's acting on the total object. We draw forces on a dot as arrows, starting on and pointing away from the dot. Meanwhile, a force diagram treats the object as an extended body. So it's drawing the arrows where they happen on the situation. So if we're drawing a force diagram on a person, our F sub W, the weight force, happens from our center of mass. So it's going to be from like the center of the person pointing down. Example of force diagram and free body diagram. Excuse me. Let's see. We got a race car hitting the brakes. 3 forces acting on the race car. Take a second. What are they? We've got the weight force, the normal force, and friction. Whenever we have tires, we have to have friction. That's what allows for motion, right? The traction. Left diagram. Force diagram. Forces start where they are applied. In the right diagram, this is the start of a free body diagram. Forces are going to come from a dot. So here's our force diagram. We know the weight, mg, or F sub W, comes from the center of any object. So it's always going to come from the center, and it's always going to point down. Notice how big it is. It's a heavy car. It's a big boy. And then it is clearly labeled, right? The car is slowing down. I think it's a safe assumption to assume the car is moving forward and then hitting the brakes, right? So if it's hitting the brakes, that means we're traveling to the right. Friction is going to go in the opposite direction. So that's why friction is pointed to the left. Then we have the road. The road is the normal force. The normal force acts wherever there is a contact between 2 surfaces. Well, we have contact between 2 surfaces at all of 4 of the wheels. So this shows just 2, but that's because this is only one side of the race car. So we have a small normal force here and a small normal force here. That means the weight is going down and the normal force is going up. So that means all of your downs should equal all of your ups, as long as this race car is not sinking or floating. It's not sinking or floating. So that means, and the floor is not about to break. So that means up, up. If we add up these two normal forces, we're going to get the same magnitude as our weight force. Now, if this were on a grid, you have to be super careful and draw each arrow the exact size. So let's say the weight force, we drew it down 4 blocks. Then this would be 2 blocks, and this would be 2 blocks. So we could easily, in our heads, see that 2 blocks plus 2 blocks equals -4 blocks. Free body diagram. Everything is taken from this and just shrunk down to a small point. And now you can see 1, 2, 3, 4, 5 for our normal force. 1, 2, 3, 4, 5 for our weight. Those two cancel out, so we know the object is not moving up or down. And then there's a frictional force to the left. Well, frictional force is going to happen when there's some kind of motion. So we must be moving to the right. There's a frictional force to the left. Just by looking at this diagram, you will soon be able to determine that this object is slowing down. Because remember, if velocity is in one direction and your force, your net force, is in the opposite direction, then you're slowing down. The weight force acts at this car's center of mass. On the free body diagram, we combine all the normals together. Generally use the simpler free body diagrams unless we need to talk about where the force acts on an object. More complicated example. Somebody leaning against a wall. On the left, we've got, on the right, there's a free body diagram of all the forces acting on the person. There's a frictional force acting down here. We've got surface contact here, pointing away from the surface to the right. We have another surface force down here, pointing away from the surface. Then we have the weight. The frictional force is by far the hardest one to see here. But without friction, this person's going to slip. It's going to fly away. That's it. We're going to do, I don't think there's even any test your understandings. I think that's it. Until next time. Be brave. Stay wild. We'll see you on the next adventure.